Give me the participants list. There we go. So does this tell you when I started the chat, or you all, or started the call, or do you all just assume 5 minutes before is a good time?
Just assuming.
Right on.
Yeah.
Because that was just like, there was just me, and then there are suddenly 10 of you. Oh, I see you came here early. Yeah, so I have it set to not actually let people in until I am here, but I'm gonna pretty consistently try to log in 5 minutes before we start. So yeah, so what, I almost said 12:55. 1:55 is a good time. Although I won't actually like start until 2, so you don't need to show up early unless you wanna ask stuff or whatever. Just get situated. First week going well so far?
Yeah, pretty good.
Right on.
How's your day, Professor?
It's warm in Northridge again. It's already 97, so I'm just trying to cool. East-facing windowed apartment where all of the heat just comes in first thing in the morning. Are a lot of you?
Yeah.
Oh, sorry, go ahead.
Yeah, one of my older got like no wind. It was terrible.
Are a lot of you still in the valley-ish, or are a bunch of you out of town for the semester, or I guess at home?
I'm still in the valley. I kind of live here at the moment.
Yeah, when I took this job at CSUN, I was like, I don't want to have to drive in LA every day, so I moved to Northridge. But I have to deal with the weather consequences. All right, it is now 2. And again, I'm going to try to stick as close to everything as we can, just for everyone's own schedules of having to hop between meetings and meetings and meetings. But anyway, welcome back to Geology 101. Is there anyone in here now who was not here on Monday? All right. Cool. So then I don't have to go back over any logistical stuff. Although, again, if you have questions about that, like feel free to ask or feel free to email. So yeah, just some updates on logistical things. So the first YouTube video of our first lecture is now up. So I know last time I was saying, check sometime after class for those if you want to see them. turns out that they take a while to upload on my internet connection at home. So if you're going, I mean, I guess you're here, so you're probably not necessarily checking the YouTube immediately. But if you do decide that you want to look at some stuff right away, I would say check back in the evening after class, because it definitely took several hours for that to upload on my home connection. So I'm sorry about that. Other logistical things. Again, this is the book that we are going to use. So hopefully you've at least ordered it or picked it up or downloaded from the website or whatever, found some way to acquire that book, because we are going to start actively using it next week. So the first vocabulary-based matching assignment that's going to require looking at the book for definitions is going to be due on Monday, right before class. So definitely, if you've ordered the book and it isn't here by a time where you can do that, please let me know. Like, please contact me. But otherwise, unless I will keep that Monday, but depending on when you got the book, that one might be a little bit flexible. But just again, let me know. So that'll be up shortly after class. Also, the first quick quiz will be up shortly after class. I was hoping to have that up before class, but I'm trying to get Canvas to do what I want, which is not always easy. So if you remember when I introduced the quick quizzes last time, I said that they're going to be, each question is going to be worth 2 points. And so even if you get it wrong, you still get 1 point. And if you get it right, you get 2 points. But I'm having a hard time getting Canvas to do that. So I'll still put that question, I'll put the questions up right after class today, but it might be that the automatic grade that it gives you is not actually what the grade will be, and I'll have to go through and change it. So I'm gonna maybe fight with it for like another hour after class to see if I can get it to do what I want. The last time I taught this class, we did it kind of with clickers, so it was just in the classroom. So it might be that, like, if you get it wrong, it'll say that you got a 0, and then I'll go back through it after the due date, which is, again, Monday, right when class starts, and update it so it'll be correct. So if it tells you, if I don't get it fixed within an hour, I'm just going to put it up there, and don't panic if it says that you have a 0. That will turn into more than a 0. But I'll let you know. So, and again, with the quick quizzes, so this one has 2 questions. So that means that you will have a total of 3 minutes to do the entire thing. But again, it's 2 questions. The point is just like, what do you remember about these major things we talked about? And it will say, it'll explain the answers once you're done with the quiz. So I definitely recommend looking back at the explanations of what's right or wrong after you do those, just so we're in good shape. So any questions?
Wait, when is the quiz again?
So I'm gonna put it up probably about an hour after class, just because I was hoping to have it up already. But that will be due on Monday at 2 o'clock. So the due date will be the moment that our class starts. And those are gonna happen pretty much before every class from now on, but they're gonna be like 1 or 2 questions. So they should, if it's 2 questions, you will have literally 3 minutes to do it. So they should take a very, very small amount of your time. So please do get in the habit of checking Canvas like a lot, because there's going to be, all of our assignments are going to be on Canvas, all of the vocabulary matching things, all of the quick quizzes, all of the assignments that aren't those, they're all going to be on Canvas. So just get in the habit of, again, maybe checking Canvas, when you think you want to do those things. I would say maybe not 1 hour before the next class. I would give yourself more time than that. But just sort of, I would even maybe schedule, like, check Geology 101 Canvas at this time, and then you can do the vocab matching and the quick quizzes. Does that answer your question?
Yes, thank you.
Any other logistical anythings before we get started? Also, starting with this lecture, there's going to be a sheet of bullet points that is on Canvas. And so again, I showed you this dead tree version from the last time I taught this class. But these are also going to go up on Canvas. So I apologize that the one for today didn't actually get posted until about 45 minutes ago, because when I post things, I have to both upload them and hit publish, and I admit that I forgot to hit publish. But if you go to Canvas right now, which I recommend you doing if you haven't already, there will be a tab that says note-taking / study guide for this lecture. And so if you open that, it'll tell you the stuff that I really want you to be solid on. And so that'll be the kind of thing that later when we're actually reading chapters, again, there's some sections where it looks like, oh gosh, there's 5 chapters on that test, but it's really only going to be sections of each chapter. And so that note-taking / study guide will let you know which stuff I'm expecting you to know from those chapters. So yeah, that is up on Canvas now. Can anyone confirm that you can actually see it?
Yeah, it's on there.
Awesome.
Yeah, I can see it.
I
Is
don't,
it the time and age bullet point?
yes. Oh, did it not change the file name? I tried to change the file name. I'll fix it. They will say note-taking / study guide. That is what I hope for them to say. But if it says bullet points.doc or whatever, that is the correct file. Cool. So that said, let's get going. So I guess it feels weird to be talking about the passage of time in a year when the passage of time is felt completely nonlinear and nonsensical. But you really can't talk about geology without talking about time. And it really is a lot of putting together the stories of geology, of looking at a landscape and going, this is what happened in this order, comes with having a sense of geologic time. And there are a couple ways to think about that, which we'll get to in a second. But geologic time is vast. So the Earth is 4.6 billion years old. And so if you think about that entire time span of the Earth's existence as being a single 12-hour clock rotation, or I guess 1 hour even. So if the Earth forms at on the hour, it forms as a molten ball of all kinds of stuff mixed together, then just by 1 second in, you already have solid rock on the surface of the Earth. And so already by then, a lot of the geologic processes that we're going to spend the rest of this semester talking about started that early on. Meanwhile, just to give us a sense of where we are at 11:59, or I guess at 59 minutes and 59 seconds, that's when modern humans evolved. That was the first Homo sapiens. So we are super duper newbies when it comes to the Earth. Geology has been doing its thing. Well, I guess I shouldn't say geology, natural processes, because ology implies the study of. But all of this stuff that we're going to be talking about in this class has been going on for billions of years, and we have only been observing it for a teeny, teeny, tiny fraction of the existence of the Earth. So yeah, even if rocks started forming at, the 1 second mark, the oldest rocks that any human has actually found, the oldest rocks on the surface of the Earth, are still at that 10-minute mark. First life, still pretty early, less than 15 minutes in. Meanwhile, again, anything with bones didn't happen until already almost 10 minutes to the hour. So there's a whole lot of time in here. An hour can feel like a million years when you're in, say, a lecture that seems new to you, but there's a lot going on. But just this, framing it this way also kind of shows the amount of time between things. So like a lot of stuff happens really quickly, like going from, fish to amphibians to reptiles to dinosaurs to mammals to birds. That's all within, 5 minutes of the clock. All of those really big steps forward in life happen in a super small period of time. Meanwhile, you've got this time from like 10 minutes in, or this time from, 1737 where you get bacteria to like 51 minutes where you get jellyfish. These bacteria, these like single-celled things and just rocks, they're just vibing for like 45 minutes. But at the same time, these 45 minutes, which represent billions of years, there's still a lot of subtle changes in the rocks. And there's still a lot of things where even if life isn't necessarily telling us what's going on in here, rocks are. And so certainly life science can tell us some things about the history of our planet, but geology is especially thriving. Whoops, come back. No, in this long section where evolution is a lot slower. So that's an important thing to think about with geology, but also kind of a thing to think in mind is to keep in mind is that sometimes you do have a lot happening at once in geology. Sometimes you can have a rock that represents a whole bunch of really big events in a pretty small period of time. And sometimes you can have a rock that looks super boring, is all made of the same stuff and the same texture and is the same color, but can represent several million years of just hanging out doing nothing. So very much like the year 2020, where, you know, all of our months are about the same length, you know. Even February was longer this year. But from the grand scheme of what 2020 felt like March and April felt like 200 years. And, you know, June felt like 2 seconds. So it's this idea of relative amounts of time for things to happen, or you can have a lot happen in a chunk of time, and you can have very little happen in a chunk of time. That sense of things is important in geology, because it's not necessarily that like every rock that took 1 million years to form is going to be the same size or the same density. There's a lot of variation, and so that's why when we talk about time, it's not just really like discrete exact chunks of seconds, minutes, millions of years. It's wiggly. Time is definitely it's not fake, but it's definitely flows in a sort of stop and start way, kind of like 2020 has. So more often when we talk about geologic time, we think of it as a linear progression, which time is. There's no going back in time. And so that progression that we wrapped around a 1 hour span on the previous slide, actually it's this 4.56 giga-annum. So you're gonna see these abbreviations a lot. So giga-annum means a billion years. And mega-annum is 1 million years, and kilo-annum is 1,000 years. So these abbreviations, these GA or GY, MA or MY, KA, you're going to see those a lot. You're going to see them in the book. When I'm talking out loud, I'm not going to ever say giga-annum, although I guess that's kind of more fun to say than a billion years, but I'll say a billion years. But just those are abbreviations to know because you will see them. But yeah, this whole time scale is in, you got 4.6 billion years. And life, the first life is about, 2.6 billion years ago. Or sorry, go back. It's close to 3.75, 3.8. The first confirmed cells are 2.6. But again, in this whole period, there's just a lot of time with not much going on in terms of life, but a lot going on in terms of rocks. So these things, so the moon formed pretty early on by a giant space rock hitting the Earth and busting part of it off. The Acosta gneiss is just a specific very old rock that people have found. The Jack Hill zircon is a particular very old mineral people have found. Late bombardment is a bunch of space rays hitting the Earth, changing some of the chemicals. So all of these are just milestones that people have identified to really go, yeah, we know this is this old, so the Earth has to be older than that. So this is just a long, long progression. And so when you're talking about the Earth, when you're talking about periods between milestones, you might be talking about millions or billions of years. And the stuff that we're going to talk about in here, we're not going to be so much focusing on any particular period in here. But I just show you this to give a sense of this is the whole time frame we're looking at. Most of the stuff we're going to talk about, as it turns out, could have happened in many of these time periods. As we'll talk about more in just a few minutes, things that happen in the 4 to 3 million range pretty much happened the same way as in the 2 to 1 million range, pretty much the same way as now. The only difference is that there's different stuff around. And so it's going to react to those processes in different ways. Does that make sense, sort of? Going to elaborate further in a minute, but. So we are dealing with 4.6 billion years. But as much as I just talked about processes and cycles, that actually brings me to a point. Most of the stuff I'm going to talk about in here, not just today, but like all semester, would love for you to be thinking about it in terms of processes and cycles. So just plain memorizing something is, I mean, you might remember it for a little bit, but if you think about it in terms of like what makes that thing happen, not just what is that thing, you're going to be in awesome shape. Like if you can remember sort of what leads to what leads to what, you can actually back the answers out, even if you don't necessarily like remember the word for it. If you can remember what happens to cause the thing that you see, you're going to be in good shape to describe it. You're going to do well on things. And so there's going to be a lot of cycles and a lot of processes in this class. That's also kind of why I mentioned we're going to be talking about the physics and chemistry of the Earth as pertains to the history and future of the Earth. Physics and chemistry are all cycles and processes. They're forces acting in certain ways that repeat under certain conditions. So again, we're going to be thinking about not just the what, but the why. And so that's also partly why later today, there's going to be some big words, but they are big words that identify processes that we're going to come back to again and again and again. But I don't want to get ahead of myself. So yeah, just take note of these abbreviations. They will come back. So yeah, these different processes, they have different timescales. So getting used to geology, some of it is used to conceptualizing that 1 million years is actually a small amount of time. But on the other hand, some of geology is conceptualizing rocks can move past other rocks at the speed of several miles per second. So you can have stuff that's super duper slow and stuff that is crazy ridiculous fast. So if the history of the entire Earth, that's not a cycle, that's a linear progression. That's in the billions of years. But when we're talking about continents moving around, which we're going to start talking about in depth next week, the movement of continents happens on the time scale of hundreds of millions of years. So I guess you can have small visible changes in the tens of millions of years ranges. Like if you were to take a map of the continents now and a map of the continents 10 million years ago, it would look a little bit different. If you went back 100 million years, it would look a lot more different. And so the movement of giant chunks of rock is you know, again, 100 million years is kind of what you're dealing with as sort of the basic unit for that. And 1 million years is super short. Similarly, when you're talking about the speed at which rocks form, some of them might form in millions of years, like with sedimentary rocks, which form by just particles of stuff piling and piling and piling up until they get compressed together into a rock. That can take millions and millions of years. But some rocks, like the ones that come out of volcanoes, can form in literally seconds, you know, minutes. Because as soon as that liquid stuff spews out of the volcano, it hardens in the air. The second it hardens, it becomes a rock. So usually when you're talking about rock formation, it's more in the millions of years scale. But even that can be pretty fast. Then when you're talking about just how landscapes get their shape, things like rivers eroding out valleys, or mountains forming and squishing together, or, you know, all kind, you know, hills turning into mountains, other hills eroding down to flat. That can be, those are generally in the millions to hundreds of thousands of years. Usually that stuff is, it's faster than the movement of continents. It's faster than the formation of rocks. Things like the Hollywood Hills have been around for, I think they're only, those rocks are older than the hills, that the hills are, I think, only a couple 100,000 years old. So those formations from being flat to turning into hills, couple 100,000 years. sometimes it can take longer. Sometimes it can be a few seconds. Like, let's say, you know, Mount St. Helens. Have you all heard of Mount St. Helens? So what did that do? Yeah, it erupted catastrophically. It blew a third of itself into oblivion. So in that case, it went from being a nice, tall, pointy mountain to a much less pointy, much less tall mountain in like a second. So some landscape shaping processes take millions of years, or very slow and gradual. Things like building mountains from nothing or eroding mountains down to nothing. But things like volcanic processes or landslides can be, which change the shape of the land, can take seconds. And then getting into some stuff that's faster. So things like earthquakes, landslides, volcanoes, they're not erupting or moving most of the time. So the time between those kind of processes, and they're cyclical, you know, earthquakes happen and then energy builds up and they happen again. Volcanoes erupt and then have to fill up with magma before they can erupt again. So there's cycles. And those cycles, they might be 10 years between them. They might be thousands of years between them. But so that's still, those are things that can happen within a sort of human time frame, like tens of years. Like you might remember multiple eruptions of the same volcano. Or thousands of years, maybe you don't remember it, but your ancestors remember it, or there's written or oral history in that land of the people who have been living there for thousands of years who were like, oh yeah, that definitely happens. So that's still, you know, 1,000 years is kind of a long time for one person, but fits within, well, it's definitely a long time for one person, unless you're a vampire, I guess. But it's the kind of thing that still is in a time scale that's conceptualized for humans. But for all 1,000 years feels long for a human, it's actually kind of long for a volcano, depending on the volcano. But it's really short compared to the movement of a continent. So this might feel a little bit dizzying, but that's kind of what geology is big cycles with smaller cycles, with big processes and smaller things that happen within them, kind of loops within loops within loops of things happening and affecting each other. And then getting into the really fast stuff, like again, earthquakes are so fast. There might be hundreds of years between earthquakes, but when they happen, you have rocks moving at speeds of literally several miles per second. Not even the fastest sports car is gonna go faster than that. And then you can have, you can have landslides that are instantaneous, landslides that take several years. You can have volcanic eruptions that are just boom and it's over. Or you can have something like the last eruption of Kilauea in Hawaii, which I mentioned last time, that started in 1983 and ended in 2018. 2019? Recently. I think it was 2018. See, I feel a little bit like a hypocrite when I can't keep track of what time it is, what day it is, talking about time. But again, just this concept of what is a big amount of time, what is a small amount of time, is going to be useful in this class. And definitely when I talk about different kinds of rocks, different kinds of landscapes, different kinds of processes, I will talk about the amount of time they take. So this isn't going to be something you hear once and never hear again. But just sort of get used to the idea that in some cases, 1,000,000 years might as well be snapping your fingers. So does that make sense? And also worth noting, if I say, does that make sense? I'm not going like, it better make sense or else. That's definitely your time to say if it doesn't. But cool. But yeah, this is going to come back. Everything's going to come back. But yeah, this might seem like a lot. It's a lot of time, 4.6 billion years. And there's a lot of different senses of time, different things moving at different speeds inside of that. And yeah, it can seem overwhelming. And that's definitely the reason we're doing this first is getting used to a concept of the amount of time things take is important for understanding the story of the Earth and for interpreting, for using rocks to interpret that. Yeah, it might seem like a lot, but again, the processes of geology, they're all driven by physics and chemistry, which are unchanging natural laws. They're things that work the same way everywhere. Physics and chemistry work the same way on Mars. The differences between Earth and Mars is just what's there. Like there's less there's different stuff on Earth than on Mars. So these things you're going to get different results of the same processes, because it's still all physics and chemistry. So really, even though this might seem like a lot, and even though you might go, wow, these rocks from 4 billion years ago look super different from these rocks from 4 million years ago, which is going to be true, because the stuff that existed on Earth 4 billion years ago, it was a lot different than the stuff that existed 4 million years ago. So you're going to get very different looking rocks, but they're still all governed by the processes of physics and chemistry. So that's why we're going to frame it in that way. Again, so even though there's a whole lot of geologic time and a whole lot of different things happening, it's just the same processes happening in different ways. So like, let's say you want to, let's say you've had a lazy summer and you ate a lot of chips on the couch and didn't vacuum very much. Your vacuum cleaner is going to have a harder time vacuuming that because there's more there. Meanwhile, like, let's say you've been really on top of it and you've been vacuuming every day. It's still the same device. You're still cleaning the same floor with the same tool, but it's going to be easier. It's going to go more smoothly. The vacuum is going to collect different stuff because the conditions are different. So it's kind of the same situation here. It's just different stuff, but same things happening to it. And there happens to be a fancy geology word for that. This is a really core premise that was first articulated in the late 1800s. So people have been looking at rocks and collecting rocks for a long time. But geology as a really observation-based and interpretation-based science really kicked off in the second half of the 1800s. And so saying the second half of the 1800s is, actually we'll get back to that, what that means. But yeah, there is a fancy word for this, and that word is uniformitarianism, which is one of the largest syllable words you're going to get in this class. But this is a super important concept. What uniformitarianism says, that is a 9-syllable word. What this 9-syllable word says is basically the same stuff that's happening on Earth now is the same stuff that has always happened on Earth, and it goes at about the same speed. So it's basically this premise of what is now always was. This is a kind of 19th century way of saying it's driven by physics and chemistry, and physics works at, you have certain constants. The Earth is spinning at a certain speed. Gravity is a certain amount. Chemical reactions take a certain amount of time to occur. So the same stuff that's happening on Earth now is what's always happened on Earth, and it's happened at about the same speed. And so what that turns out to mean is basically if you see something on Earth now, like this picture on the left, these are mud cracks in, I believe this is Death Valley. And so this is dirt. This is not rock yet. And this forms by basically wet dirt drying out and compressing. And so these cracks happen when the water that's holding these dirt particles together gets evaporated and it just contracts. And so this is a thing that we see happening now. This happens on a yearly basis in places with the right climate. But then on the right, this is a rock. This is an old rock. But you see how there's similar cracks and patterns in it? Oh yeah, did I say that this all happens at the same speed? So sort of, roughly. So that's a really good question, Jade. So in general, they're gonna happen at mostly the same speed. So like, let's say you, using this mud crack example, like if let's say you have a particularly wet year and there's a lot of rain, it might take more time for that water to evaporate and therefore longer for the mud cracks to form. Or let's say like you have a normal amount of rain, but then it gets even drier than usual, those mud cracks might form a little faster. So the specific conditions, the details of the conditions will affect the speed of things, especially on the surface of the Earth. But especially once you get deeper inside the Earth, the surface conditions matter less and less, and things happen at more and more of the same speed. So does that answer your, okay, cool. That does answer your question. So that's why we say it's about the same rate, but not exactly. But yeah, what this then says is if you see something on the right, see something in a rock that looks like these mud cracks that you see in the current modern Earth, and especially if you were to actually analyze this rock, you would be able to tell that it is just the same kind of particles that are in this dirt, just stuck together as rock. There would be, I mean, you could come up with a much more convoluted story about how this got like this. But you could also just as easily, more easily go, well, this looks like it used to be made out of mud and it has cracks in it. So why didn't it form the same way that cracks in mud form now? So basically it's this baseline assumption that things work in the same way. Now there's always going to be that exception to the rule. There's always going to be something that might look like something else and then turn out to be something completely different. But in order to, that's the kind of thing where it's kind of you're innocent until proven guilty. You have uniformitarianism. You have the same thing happened in the same way, until you can come up with a lot of evidence for proving otherwise. And so that's kind of why geology can be detective work. You can start with this baseline assumption of, be like, yes, this is what happened, and then maybe it is what happened, and you can collect more details about what happened. Or sometimes you find some piece of evidence that goes, actually, this isn't what happened at all. So that's why just looking at the details and seeing, do they agree with this assumption, or do they not? That's kind of one of the first steps. So are we good on that? I will bring this back up again and again and again. Everything that we're going to talk about today is going to keep coming back up. So, cool. Let me advance the slide. Cool. So when we're talking about age, there's actually kind of a couple ways that you do that. So absolute age is just how old something is in units of time. So this is what I was starting to hint at on a couple minutes ago when I said, in the late 1800s. So saying the late 1800s is an absolute age. It's like, we know that's when that was. We know that something happened in the late 1800s is like 100 and, 120 years old at least. Meanwhile, relative age is how much older or younger something is compared to something else. So, and in that case, like if you were to say this was the beginning of modern geology, that says that it's newer than what people were doing before that, but older than how we're studying geology now. So it's kind of, so to give some examples, absolute age would be like, I'm 36, my brother is 32. Those are numbers in units. Relative age would be, I am older than my brother. Doesn't necessarily say how old we are, just I'm older than him. An absolute age would be saying that thing happened in May, period. A relative age would be like, I don't know, I guess that happened after the lockdown started, but before it got really hot. So those are two milestones. Like, we know that the lockdown started at a certain time and it got really hot at a certain time. And there's kind of this gap between that when this thing could have happened. Yeah, relative it's kind of an estimate, but you're not going to give relative time in units. Like, you're never going to, and when you might give even a range of years is still, anytime you're putting a unit on it, it's absolute. So if you were to say it was like, if you were to say something happened between 10 and 15 years ago, that's still an absolute age. It's just not a completely certain one. But if you were to say, oh, that happened like before I graduated from high school, that's a relative age, because graduation from high school is an event, not a time. So relative age is a comparison more than it is an estimate, whereas absolute age has a unit on it. Does that answer your question? Wow, did a red dot just pop up on anyone else's screen? But Diana, does that answer your question? Cool. Yeah, so like another example is an absolute age is this rock is 36 million years old. A relative age would be this rock formed after the inland sea dried up, but before the volcanoes activated. So again, we might not know when the inland sea dried up and when the volcanoes activated, but we can tell from geologic inference that this rock has to have been between those things. And so honestly, for most geologic thinking, relative age is actually more important. Most of the stuff we're going to talk about is going to be in terms of relative age. And actually, most of the history of the Earth, as we know it, got pieced together through relative age and then later confirmed by some sort of way to get absolute age. So a lot of it is like you're going to find a bunch of rocks and you're going to go, what order did these rocks get there in? In what order did these things happen to these rocks? And so then you can come up with a story of this happened, and then this happened, and then this happened. And so even if you don't necessarily know if it happened 1 million years ago or 1 billion years ago, you can still go, okay, in order to get this like it was, this happened, and then this happened, and then this happened. So there are ways to tell absolute age. And so have any of you heard of carbon dating? Cool. And does anyone want to try explaining, or like, how does that work? Carbon dating. Or is it just something that you've heard of and we're never quite sure what it was? So carbon dating, okay, I think it's one of those things a lot of people have heard of, but don't want to know what it is, and don't feel bad about that. It's the kind of thing, like, it's a sciencey term that ends up in like movies, and it also can be used in forensics. Yeah, you heard it, but don't know how to describe it accurately. So we're not actually going to get a lot into that here, or even much into absolute age. But basically, carbon dating is saying carbon atoms over time will change their structure. They'll change from having a certain number of neutrons to having a different number of them. And so you can go the rate at which, like basically the proportion of how many of the mutated is the wrong word, but the pristine carbon atoms versus the decayed carbon atoms. You can do a ratio and go, okay, if there's this percentage of the pristine ones and this percentage of the decayed ones, you know it must be a certain age. And so that'll make more sense when we talk more about chemistry later. But you can do similar things with other atoms. Like carbon dating doesn't work for really old rocks, but the same thing applies for a lot of other atoms. And so you can do that to get relative age. You can also actually do carbon dating or things on fossils included in rocks to figure out how old those rocks are. But that kind of happens later. Generally, when coming up with a geologic history, you're going to come up with a relative age, a sequence of events before you come up with an absolute age. And also to that point, in this class, obviously we can't find absolute ages without being in a lab with equipment, which we definitely are not. But all of the times when I'm asking you about a geologic story in this class, it's going to be about relative age. I'm going to want to know the order in which things happened. But I don't need to know when exactly they happened. So really, relative age is the real guts of this. So if you were to look up geologic time, oh wait, sorry, skipping order. So another key principle of relative age and of geologic time is just that something has to exist in order for something to happen to it. Like you can't do something to something that isn't there, which should hopefully be painfully obvious. But a lot of the times, again, in geologic thinking, just by thinking of the most obvious solution first, the most obvious, simplest thing first, is a really good start. So like looking at this obvious stock image, what has to have happened here? Like, what is the sequence of events that led to the situation in this picture?
Someone tore up the paper.
Yeah, so someone tore up the paper. And then what?
Dropped it on the ground.
Yeah. So they tore up the paper and then they dropped it on the ground. And so you couldn't have torn up the paper if it didn't exist. You couldn't have dropped it on, I mean, you could have dropped it on the ground and then torn it, but probably they didn't. So in this case, you can't tear the paper before the paper exists. You can't drop torn pieces without tearing them. But also you can't drop them on the floor if the floor isn't there yet. So sometimes you even want to think about, and you can't have a printed document to tear up if you don't print it. So you can get, that's a really good take on that, Jade. So you can get into even more and more detail. So if you wanted to get like crazy detailed, you could go, these stone tiles formed, and then someone turned them into tiles, and then someone put them on the floor, and then someone built the house, someone went in the house, looked up the document, printed it, but meanwhile, someone went, bought the paper, brought it in the house, looked up the document, printed it, tore it, and then threw it on the floor. So there's a whole lot of steps of detail you could put into this. Or you could just go, someone tore up the paper and threw it on the floor. Both of those things are correct. And it just shows that you can look into geologic storytelling, geologic inference at a lot of levels of detail. But first and foremost, something has to exist in order for something to happen to it. And so even if you can't tell how old something is, if you can figure out the order in which those things happened, you can tell that story, like we just did with the previous. So in emoji speak, if we can say that this previous slide is kind of like what I have over here, where you build the house on the ground, and then you drop the papers on the floor in the house. That's one story. But if you had the ground and then the paper on the ground and then the house on the paper, that's a really different story, right? So if the paper is in the house, it's all over the house, you might go, yeah, this person dropped paper on the floor, they're a clutterer. That's the process. So that's a case of, we see these things in this order. This process, someone being a clutterer, could lead to that. Meanwhile, in the other one, you got the paper under the house. Is there a treasure map? Are they pirates? Is there some deep secret they don't want us to know about? This case, it's an order of events that can lead to a very different set of conclusions, because chances are, no matter how much of a clutterer someone is, they can't clutter like through the floor. It requires a different explanation for that order of events. And so a lot of geology is going, here is the things that happened in this order. What has to have happened to put them in that order? So cycles, processes, repeated events. So if you're going to look up geologic time, you would see this thing. And so this is, we are not going to memorize this. You do not actually need to worry about this. I'm showing you this as a proof of concept. It is kind of in your book. But this is a map of geologic time. So GSA is the Geological Society of America. This is their most recent version of the geologic time scale. And it's structured, well, how is this thing structured? Like, don't worry about the names, don't worry about the colors right now. I guess you can look at the colors, but just how is this chart structured? So let's look at just this third column, because it has the most color difference. So look at the different colors and look at the different widths of these boxes. Yeah, varied columns and rows. So this thing is actually so that's totally right, Brianna. And we want to take a stab at what these columns and rows might be.
Would they be like periods of years and stuff like that?
Yeah, so they're
millions and stuff.
Sorry, go ahead.
No, I'm just saying, like, it looks like a bit of like a time chart of within like periods and like eras and stuff.
So this is absolutely that. It is absolutely a chart of time. But why is it in a stack and not in a line? What do you think?
It's like the example of the house in the paper you showed us. Like, that's how the story is.
Yeah, exactly. So in this case, the reason this is divided up this way is not only is it sequence of time, but it's literally layers of the Earth. So these things are not just, they're actually saying that these sections of rocks are in this time. And so you might notice these are not all the same width, even. So like this might be that a Visayan rock, I'm actually not sure I'm pronouncing this one right. But a rock from this section of the time scale might be thicker than a rock from this Kazimovian or Rhodian. I can pronounce Rhodian. And it also would mean that going from bottom to top, you're always going to find the Visayan is always going to be below the Moscovian, is always going to be below the Kungurian. You do not need to know those names, just as an example. So this is a way to represent time that also represents the very literal layers of the rock that people used to determine this time. So remember how I showed you that picture of the Grand Canyon on Monday? And how we talked about how those layers are like opening in a book into the story of the Earth? So the Grand Canyon is a very literal, like you could hold up the section of the time scale that represents the Grand Canyon next to the wall of the Grand Canyon, and you would see the same relative layers. Because this is a graphical way, a time-based way, especially a relative time-based way, to show how these layers of rock have formed, in what order, over what amount of time. So there are actual ages on here because, again, there are ways to do absolute time. So the people have done that. But again, we're really mostly going to worry about relative. So all I want you to get out of this is really this comes from layers. And these layers we use layers for a reason. And it's because there's a consistent process associated with sedimentary rocks in particular. So I know we haven't really talked about rock types yet, and we're going to talk a lot more about sedimentary rocks in like October and November. I guess October. But basically sedimentary rocks form in layers. They form by particles of stuff piling up and eventually becoming rocks. So kind of like how, like, if you're sitting at your messy desk and your papers are piling up on your desk, just if you don't clean your desk, the papers are going to pile up and pile up and pile up. And the stuff at the top is going to be looser, but the stuff at the bottom, if you really don't clean your desk, is going to be kind of really squished together. Like how it's easier to pull a paper out of the top than out of the bottom. Same idea with sedimentary rocks. And so they're great for figuring out relative age because they always form in horizontal layers. They always form by things piling up. And they always form from the surface downward. So it's always stuff is piling up and getting compressed into rock, and piling up and getting compressed into rock. There's a lot more detail into that, which is what we'll get into later. But this basic thing is you form these layers. And if nothing is happening to them, they're going to stay as layers. And because they're about things piling up, they are forming somewhere on Earth all the time. Other kinds of rocks form more intermittently or form at a sort of stop and start way, but you always have sediment collecting somewhere. So you're always recording the passage of time through sediment piling up. And another thing is that sedimentary rocks, because they start as dirt, get fossils in them. So that's where you're going to find your dinosaur bones or your trilobites or your dead critters. And those can be useful for both relative and absolute dating. Like if you find something that's more evolutionary complex in a rock, you know that must be a newer rock than something that only has squishy fossils. And also you can carbon date them. So sedimentary rocks in layers are kind of the real basis for thinking about relative age and geologic time. and other kind of rocks come into it. They come into the picture, but usually in untangling that history, you start with the sedimentary rocks. Igneous rocks, so volcanic rocks can either be on top of them or come up through them, and then they can get turned into metamorphic rocks. We'll talk a lot more about that soon. But yeah, a lot of key geologic thinking just comes from looking at the layers and seeing what has happened to them. So for the rest of today, we're going to go through some things that can happen to some layers. And there are going to be a lot of words, and there's going to be a lot of examples. And do not worry about it. Definitely like write these down now, sort of think about them. Like don't go, oh my gosh, 9-syllable word. I think uniformitarianism is the only one that has 9 syllables. But we're going to see these things again and again. I just want to start introducing them now. So by the time we get into more specific details about specific kinds of landscapes, it doesn't sound like a total foreign language. Because in a way, at the beginning of any new subject that you've never had before, you can kind of think of it as a foreign language class where these are words you don't know and you don't know what they mean. But the more you hear them and the more you use them, the more they start to mean things. And so that's why we're going to go over a bunch of these now, and then I'm going to keep bringing them up through our lectures through the rest of the entire semester. So write them down more than once. You'll eventually remember them. So it is totally okay to not get this now. It is totally okay for you to be like, this class might as well have been in Russian. But it will come back. You will be okay. And if it's not okay, ask me. It is always okay, either in here or in office hours or an email or whatever. And again, a tip while you're thinking about these, knowing the word is good, but knowing what it means is more important. Like if you can describe what happened and don't necessarily remember the word is worth like 1 point. The history, the entire telling the story is going to be worth like so many more points. So just think about it in terms of processes, not just what is it, but why is it? Cool. Are you ready for some geology words and some pretty pictures? Because one of the things I love about this also is that, the land is beautiful. And just being able to look at a pretty thing and go, yeah, that's why that happened is even more amazing. It's sort of the difference between knowing how to appreciate art and knowing how to make art, kind of. So you're not making rocks, but there are actually some labs where people make rocks. It's pretty cool. We're not doing that. I digress. So we talked about uniformitarianism, and we talked about how sedimentary rocks form in layers. So there is a fancy word for that, or a fancy term for that, which is original horizontality, which means they form in layers. Horizontal, flat, original, started that way. A lot of these terms are really literal, so that's good. Even if they're big, they're literal. So this picture on the left, which I admittedly forget exactly where this is, I think it's a desert in Iran, but I might be wrong. Nice, flat, horizontal layers, really colorful. This red means there's a lot of iron in these rocks. So for the same reason that iron and steel, non-stainless steel can rust and turn red, rocks with iron in them are usually really red. And so in this case, we see lots of layers of lighter or darker red or pink or white. And this means that this stuff was piling up. And this also means this is pretty undisturbed because it's still in these layers. This is kind of how it formed. I mean, obviously there's been some erosion because you can see it's a hill and not just totally flat. But these things they formed this way and they stayed this way. Meanwhile, on the right, this is in Palmdale, a lot more close to home. But these are all sedimentary rocks. And is there anything even sort of horizontal happening here?
No.
Not at all. Yeah. So what do you think happened?
Maybe rain.
Oh, this is, so rain actually is going to aid in the formation of more sediment. So rain is also falling on the flat ground. So I see someone says earthquake. So yeah, this is, so you're totally right, Brianna. So rain is useful in forming layers. Rain is part of the process on the left. But earthquakes happen to be the thing on the right. So this is right next to the San Andreas Fault. This is on the 14, right past the Avenue S exit, if you want to go see this. If we were in an in-person class and could do field trips, I might take you to see this. But basically, these formed flat. And over time, the movement of the San Andreas Fault squished them into these crazy twisted shapes. So basically, sedimentary rocks form like the situation on the left. If you see something like the situation on the right, that means something has to have happened to really screw up those layers. But those layers have to have been there first. You can't fold layers over like this if the layers don't exist. So if you see something like the picture on the right, you already have two steps. The layers formed, and then they got twisted. Make sense? So just a fancy term for a basic concept. Another thing we already talked about that has a fancy term is this stuff piles up on top of each other. Sedimentary rocks always form, they start by stuff piling up, and then stuff piles up on top of it, and stuff piles up on top of it. And so the fancy term for that is superposition. Basically says every layer forms on top of the previous layer. And therefore, every layer is younger than the one below it. So kind of like if you think about, again, those papers piling up on your desk. Chances are the papers at the bottom are going to be the oldest, right? Like you're going to drop the newest papers on top. And so if you were to pull a paper out from every level of the clutter on your desk, you would be pulling, they would get older and older and older as you went deeper. And that's exactly the same with rocks. And so the oldest stuff is going to be at the bottom in an undisturbed setting. So sometimes you might find a situation where the oldest stuff is not at the bottom. And that means that something has happened. Something has happened to flip things over. So sometimes, so this is another nice, beautiful, flat set of layers. You might see things where, rather than them being horizontal, you see things that are at like a 45-degree angle. And then you have to go, okay, they're at an angle, something tilted them. And then you want to see, are the ones over here older, or are the ones over here older? Because if the ones on this side are older, that means that was the surface of the Earth, and it got tilted this much. But if the ones that are over here are older, that means this was the surface of the Earth, it got tilted a whole lot more. So by figuring out which way is up, i.e. which end is younger, you can start to figure out what happened. But when in doubt, until proven otherwise, if you see something that's beautiful and flat and horizontal, the older stuff's going to be at the bottom. So like with the Grand Canyon, the old stuff's at the bottom. Hopefully pretty straightforward. And so this is a case that eventually I'd love you to know the word superposition. But even if you don't remember that word and can just say, yeah, the older stuff is at the bottom and the younger stuff at the top, that's the important part. Moving on, here's another, this is kind of expanding on both of those things. So here we have the Grand Canyon again. So the idea of a lateral continuity basically says that stuff is going to be the same over a large distance. Stuff is going to be pretty continuous for a while. And especially because of how sedimentary rocks form. They form by stuff accumulating. And actually, they tend to form at their fastest in places where there's a lot of water. So we had that example of rain earlier. In places that have a lot of rain, you get them forming faster. Or in places that are underwater, they form even faster because you just have a continuous amount of stuff trickling down and piling up on the bottom of the water. And so generally, a lake is going to be pretty big. An ocean is going to be really big. An area that's experiencing a rainstorm is going to be big. And so often those layers that you form are continuous over a really big area. So the rocks in the Grand Canyon are actually, they're just exposed, but that whole area, it's called the Colorado Plateau. And it expands over several states, over Colorado, over Utah, over Arizona and New Mexico and parts of Nevada. And that actually all used to be underwater. That used to be an inland sea, but now it's a desert because continents move. But if you look at the rocks on, in this chunk versus in this chunk, they're the same, right? Like you can see here's this dark red one that matches up with this dark red one. Here's this lighter one that matches with this lighter one. Even though there's a big gap, there's a Grand Canyon. It's the same stuff on both sides. And so what this says is if you got a discontinuity like this, and you've got the same stuff on both sides, the stuff has to have formed before the discontinuity formed. So in this case, it wasn't like, hey, you got a river, and these rocks were forming on either side of it. No, this was a case where the rocks formed, and then the river cut the separation between them. Does that make sense? So pretty much anytime you see stuff and a break and the same stuff, the break has to have happened after the stuff formed. And that's actually true for more than just sedimentary rocks. Basically, if you see two totally unrelated things next to each other, they're either one of them got moved there, or you're actually at the boundary of two processes. So this example on the left, can you see how there's this kind of bluish rock next to this yellowish rock, and there's a really clear line? So in this case, these rocks were not next to each other, and a fault over the course of many earthquakes moved those next to each other. So in this case, there's no lateral continuity because things got moved. And in this case on the right, you can see this very red thing in the middle of this very yellow stuff. So this red thing is a little volcano. This is in the Eastern California. This is in Northern California here on the left. And basically here you would see this very red stuff next to this very yellow stuff. It is not continuous because there's different things happening. But in general, if you see a break and stuff is the same thing, the break happened later. Or even if you see a break and like you had your layers, and then you have your layers on the other side of the break that are maybe up higher, but are still mostly the same layers, that means that something happened to move those, but those have to have existed before they were moved. Sound good? So a lot of relative age, a lot of putting together the story is figuring out, okay, first, in what order did these things form? And second, in what order did these things happen to them? And so you might have a situation where like something formed and then something happened to it and then something else formed. So it's not always that everything formed and then everything happened to it. But usually like you can tell, like if you have some stuff that's, actually we'll get to that. We'll get to that in a few slides. How are we doing? We're doing well. So that was for our layers and layers. That was when you're just dealing with sediments and things happening to them. But a lot of times you can also have rocks that are molten, like magma, traveling through the earth that gets injected into other rocks, sometimes as a narrow tube, sometimes as a big glob. And we'll talk a lot more about that with our igneous rocks unit. But in this case, when you have liquid rock, it doesn't necessarily behave like a layer. It can behave like kind of whatever shape it wants. But there are still a lot of ways to interpret these because usually they're going to interact with each other, or very often they're going to interact with places where there are layers. So in this case, a cross-cutting relation. So what's going on here? What do you see in this picture? Go for it. Hold on. Whoa, it's not showing me. I saw a hand up and it's not showing me your name when I hover over you. What's going on?
Like if someone just like slashed through it.
Yeah, so it looks like someone slashed through it. In this case, someone is a bunch of really hot rock. So I guess it could be an earthbender, I guess, but in this case, it's mostly volcanoes. So what you have here is you all see this really dark band cutting through this much lighter rock, right? So in that case, in order for that band to cut through the other rock has to exist. So cross-cutting just says the thing that is doing the cutting is younger than the thing being cut. And so here, like this is probably a big chunk of sedimentary rock. You don't, or it might be other volcanic rock. It's kind of hard to tell from here. But because this is a big mass and this is a narrow thing, this has to have cut through it. Like it wouldn't make sense for if this just narrow little thing had formed and then everything else had kind of welled up around it, right? Like that doesn't even make sense from a physics standpoint. Like would something just this narrow little like rock noodle, would it even stand up if it just formed like that? Would it even form like that? It, you know, it wouldn't. There's just no force that would form a narrow little band like that. So basically this cuts through this. So this is newer than this. And you could even take this to another level. So this is obviously a road cut. You can see by these columns that are blasted out of it by people. And geologists love road cuts because it exposes the inside of things that you might otherwise not see. So in this case, can you see how these blast marks actually cut through the black thing? Like here and here. So you could argue and say the road cut cross-cuts this thing that cross-cuts this thing. So sometimes the signs are really obvious and sometimes they're more subtle. But whatever is the least cut through is the newest thing. The least disturbed thing has to be the newest thing. So another thing about really hot rock is that heat cooks stuff, and rocks can get cooked. So this is an example from, I think, France, maybe Switzerland. So this is the Alps. And so do you all see how there's this dark band here? And there's lighter gray rock on either side of it. Like most of the mountain is this lighter gray rock, but you have this darker one through it. So first of all, in one hand, that's a cross-cutting, right? Like this crosses through that. You wouldn't get this thing forming by itself. So this had to have cut through the other mountain. But also, do you see how there is, whoops. Do you see how there's lighter gray right along the edges of the darker gray? See how it's almost white around these edges? That's basically where this stuff, as it was hot, cooked the rock around it. So same idea, like you can't cook something if it doesn't exist. You cannot make tacos for dinner if you don't have tortillas, right? You can't cook something. You can't barbecue chicken if you don't have, the barbecue might be really hot, but if the chicken is there, you're not gonna cook it. It's the same idea. This rock that has been cooked has to be older than the rock that's cooking it. Good on that? This is going to come back a lot more with both when we talk about volcanoes and igneous rocks, and then when we talk about how mountains form later on. But it's not always that the thing that is inside the other thing is newer. So you can have a situation where you have a chunk of another rock in an older rock. But in this case, the chunks, if they're discrete chunks, they've got to be younger than the whole other rock. And so sometimes, like this one on the right is a sedimentary rock. And so you see you have these big jagged chunks of rocks surrounded by kind of mucky looking stuff. So in order for this to form, these jagged chunks had to have fallen in the mud, and then the mud eventually turned into another rock. So these chunks are going to be younger than the stuff around them. And in this case, so this green stuff is called peridotite. It's actually the inside of the earth, a lot of it is green. It is not orange, it is green, and it is made of this stuff. And so sometimes in a really exuberantly violent volcanic situation, as rock is erupting out, it's going to grab chunks of the deeper earth as it's coming towards the surface. And so in this case, this rock is going to be older than this because it can't be grabbed if it doesn't exist. This can't get surrounded by mud if it doesn't exist. So it's kind of whichever thing is more flowy, whether it's liquid rock or whether it's mud that hasn't turned into rock. The more solid thing inside it is going to be older. Does that make sense? So that's especially going to come up with sedimentary rocks in October-ish. So lastly, we're going to go through these. These are going to seem the most confusing because there are 4 words that sound very similar. Don't worry about it. They will come back. We will talk about them more. I just want to introduce you to these words now. Basically, if something is not there, it can tell you a lot about what happened. Like, let's say let's use your papers on your desk example again. Like, let's say on one side of the desk, you haven't disturbed the pile of papers for 2 semesters. And on the other side, you went and you took something out to look for it, but then put the other ones back. If someone were to be looking at your desk, they would go, okay, everything is here. Something is missing over here. Someone must have taken it. So sometimes the absence of rock or the absence of evidence is evidence, which is not something that would ever hold up in court, but this is geology. So the general term is an unconformity. It does not conform. It's where you have rock that is touching rock that did not form right next to each other. So it's like rather than having rock A, rock B, and rock C touching each other, you would have rock A touching rock C because rock B is gone. So it definitely takes some detective work to figure out why rock B is gone, but then you look for other stuff. There are a lot of ways to figure out why rock B is gone. So definitely unconformity is the most important word here. I'm going to go through the 3 kinds very quickly. Do not worry, they will come back. You can have one where the angle doesn't match. You can tell it's an unconformity because you'll have something that's at one angle. Like you might have, in this case, it's something that's really folded and then has flat stuff on top of it. Or you could have something that's at a 45-degree angle with stuff that's flat on top of it. Or you can even have something that's at a 45-degree angle with something that's at a 30-degree angle. And what that means is the first thing formed got changed, eroded flat, and then something else formed on top of it. Or you can have something where you just have 2 totally different kinds of rock on top of each other. You might have igneous rock, like you might have something like granite that has layers of, and granite usually doesn't form flat. So in order for granite to get flat, it has to erode flat. And so the rocks that form directly on top of the granite might be way younger than the granite because they just formed in a different way. So you're going to see that because it's going to be 2 really different things touching each other. And so nonconformity is a type of unconformity. Very similar sounding word. Don't worry, this confuses literally everybody at first. We will go back over it. And then lastly, you're going to be disconformity, which is also a type of unconformity, but not a type of nonconformity. Don't worry about it. Do not worry about it. These can be invisible though. Like in this case, you can have sedimentary rocks form and then get eroded and other sedimentary rocks form on top of it. And so it might look like a bunch of really perfect, beautiful layers, but there might be a gap of like 2 million years between layers that are touching each other. Might be a gap of even more than that. And so this is the kind of thing where it requires often absolute age is useful to tell here, or finding some other place where that layer isn't missing is useful to tell. So again, this might seem like a lot. It is a lot for day 2, but I'm giving this to you to give you sort of the introduction to the kind of language that we're going to be using all semester. I promise it will make more sense as we go on. And by the end of this class, if you're attentive, it's going to feel hopefully really familiar and comfortable to talk about these things. So with that said, we got 1 minute. Does anyone have any questions? Yeah. Okay. Okay. So in that case, again, I'll put the quick quiz online as soon as I can figure out how to get Canvas do what I want, or 1 hour from now, whichever happens sooner. Similarly, the vocab thing for next time will be up when that goes up. And if you want to see the video of this, it'll be on YouTube in a few hours because it's slow. So with that, we will talk about the structure of the Earth starting on Monday. If you want to hang out and ask questions, I'll stay online a little longer. If not, I will have a, I guess it's weird to say good weekend already, but have a good weekend.
Thank you.
Thank you, Professor.
Thank you.
Thank you.
Have a good day.
Thank you, Professor.
Thank you all for good questions, good answers, good attention. Right
I
on.
have a question.
Yeah.
Did you take attendance? Because I came in a little bit late because
I'm not taking regular attendance. I mean, I want people to, like, the advantage of coming to class is obviously you can ask questions and see things as they're happening, and you don't have to wait for YouTube to load. But I understand that especially when everything is on Zoom, things break. So
Yeah.
again, I'm not gonna check people off for attendance, but I encourage you to come because you get a lot more out of it when you can ask things and interpret but yeah, those the quick quizzes are partly basically participation grade.
Okay. All right then. Thank you. Have a good weekend.
Have a good one.
Bye. Thank you, Professor.
Thank you.